All right, well, we are picking up with part 2 of working the honors physics performance exam review. I left off last time by saying that we were done with the electricity unit, which was actually wrong because number 8 is also electricity. So we're going to jump right back in with electricity. This says, how many kilowatt hours of energy does a 600-watt toaster use in the morning if it is in operation for a total of 10 minutes? All right, so they've given us the power in watts. All right, sorry about that interruption. Okay, so we're given the power in watts, and we're asked for energy, specifically in kilowatt hours. So if we go to the formula sheet, there is a formula that says power is energy over time. If we rearrange that for energy, energy equals power times time. However, the time they have given us is in minutes. We don't ever want minutes. Usually we want seconds, but because they have asked us for the answer in kilowatt hours, we're actually going to go to hours. So to go from minutes to hours, you would divide. I don't have my calculator, hold on. It's good that I got up and got my calculator anyway, but it occurs to me that I don't actually need a calculator to divide 10 by 60. So 10 divided by 60 is going to give us 0.167 hours. Which is 1/6 of an hour, which makes sense. Now, because we want to do kilowatt hours, we also need to change power. 600 watts to kilowatts is 3 decimal places. So we're going to have 0.6 kilowatts. And now we can just multiply. 0.6 kilowatts times 0.167 hours. Gives us 0.10 kilowatt hours. So that's the answer to part A. Next it says, at a cost of 15 cents per kilowatt hour, how much would this add to your monthly electric bill if you made toast 4 mornings per week? Now, this involves a formula that's not on the county formula sheet. I will have it on the board for the exam, though. And it says that cost equals energy times rate. So our energy is 0.1, our rate is 15 cents. Now, we want our answer in dollars. We don't want our answer in cents. But luckily, it's really easy to do conversions from cents to dollars. 15 cents is going to be $0.15. So 0.1 times 0.15 hold on just a sec. Okay, sorry. So yeah, 0.1 times 0.15 tells us that every day your toaster is going to cost you $0.015. But it doesn't ask you how much for one day. It says how much per month if you're using it 4 mornings per week. So 4 mornings per week, 4 weeks in a month. We'll go over here. So that's a total of 16 days per month. So we're going to do 0.015 times 16 And we're going to get that per month the toaster is costing us $0.24, which is the same as 24 cents. None of that math was very hard, but I managed to confuse myself a little even because I thought it just said 4 mornings, and then I realized that it said monthly, so you had to multiply by 4. So just make sure you read the problems really well when you're doing this stuff. All right, now we are officially moving to magnetism. Number 9 says make sure you know how to represent magnetic field lines between 2 north poles, 2 south poles, and a north and a south. The main thing to remember when you do these is that field lines always go from north to south. So, if we had 2 north poles, we would have lines coming in towards the north poles, but they would be repelling away from each other. I didn't leave myself a whole lot of room. This is not going to be the prettiest picture, but you get the general idea. If you have 2 south poles, you're going to get the same shape, but now the arrows are pointing outward because the field lines are moving away from the south poles. Then finally, last but not least, if you have a north and a south, they're going to go from south to north. They're no longer repelling each other. Yay! Beautiful pictures. Now, number 10 says study your worksheet about electromagnetism and make sure you know how to use the right-hand rule to determine the direction of a magnetic field around a straight conductor. This would be hard for me to kind of demonstrate on camera. It would just be a lot of me like twisting my hand around. So you may want to go back and look in your notes for this section. The best I can do is list the rules. The right-hand rules for a straight conductor is you put your thumb in the direction of the current. Oh, I have not left myself enough room. You're going to curl your fingers around the wire. Let's actually go up here. And third, your fingers show the direction of your magnetic field. Again, there's not a good way for me to show that on here, so I would strongly recommend you look that up in your notes a little. All right, here is our odd man out question. This is actually a waves and sound question. It says AM radio signals have a frequency between 550 kilohertz and 1600 kilohertz and travel with a speed of 3 times 10 to the negative 8th. What are the wavelengths of these signals? A lot of people, when they saw problems like this, thought they needed to like subtract the 2 frequencies. You don't. It's basically just 2 separate problems. So we have our first frequency is 500 kilohertz, and our second frequency is 1600 kilohertz. Now, we don't want kilohertz, so we need to move the decimal 3 places. That's going to make this 500,000 hertz, and this 1,600,000 hertz. Both of them have a speed of 3 times 10 to the negative 8th because all radio waves have that speed. So to find wavelength, we would look under sound and waves again. It's the same formula we've used before. V equals lambda f. So to get lambda 1, we would do V over F1. Lambda 2 would be V over F2. So 3 times 10 to the 8th over 500,000 over 1,600,000. You could put those in scientific notation if you wanted as well. I'm not going to because I'm kind of feeling lazy right now. Oh, and I just noticed, because my answers aren't coming out quite right, that this should be 550 kilohertz. So let me correct that. All right, so I've now corrected that. I have 550 kilohertz, which is 550,000 kilohertz. So when we do this math, I'm getting 545.5. The answer key apparently rounded a little. That's in meters. For this one, I'm getting 187.5 meters. Again, apparently some rounding going on. Now, I haven't left myself a whole lot of room, but it says, how long would it take for the signal to travel 100,000 meters? So here we're just going to use V equals d over t. It's going to be the same number for both of them because notice the time is, or the distance is the same and the velocity is the same. The fact that they have different wavelengths does not actually change how fast they're traveling. So we're going to have 3 times 10 to the 8th equals 100,000 over t. T equals 100,000 over 3 times 10 to the 8th. And I'm getting, this one I am going to put in scientific notation. It's technically 0.0003, but a much neater way to write that is 3 times 10 to the negative 4th seconds. All right, now we have our last question. Oh no, we have 2 more that are magnetism. So back to magnetism. A 0.035 meter long wire lies perpendicular to a magnetic field with a magnitude of 0.4 Tesla. Calculate the force on the wire if the current in the wire is 5 amps. So length, which is L, let's see, does it use uppercase L? It does, okay. Length is 0.035. Magnetic field, which is represented with B, it's something you need to remember because it's kind of strange. B is 0.4. I is 5. And we're looking for force. Let me get the lights, hold on. Okay. So back to our formula sheet under magnetism, there's only 2 possible formulas. We're going to use the one that has stuff that we have. F equals Bill. .4 times 5 times 0.035. 0.4 times 5.035. And I am getting that our answer is 0.07 newtons. It may be a magnetic force, but it's still just a force, which means it's in newtons. All right, Now the last magnetism one. My guess is that we're going to use the other formula, barbecue V, as I call it. That offended some people, that's okay. But let's look at what we have first. We have a charge, so that's Q of 3.2 times 10 to the negative 19th coulombs. And it moves at a right angle to a magnetic field, which has a strength of 0.3 Tesla. So that's B is 0.3 Tesla. If the ion's velocity is 2 times 10 to the 7th meters per second, what is the force acting on the ion? So V is 2 times 10 to the 7th. That is very fast. And we're looking for F. We are, in fact, going to use F equals BQV. F equals BQV. So 0.3 times 3 times 10 to the negative 19th times 2 times 10 to the 7th. We should be able to see right away that this is going to be a very small number because negative 19th is much smaller than positive 7. Be careful as you're plugging this into your calculator. It is easy to confuse your calculator when there are like multiple exponents happening. It's not as bad in this problem since everything is multiplying. It's much worse in problems where you're dividing. It's 3.2. I am just messing up all over the place. All right, so 0.3 times 3.2 times 10 to the negative 19th times 2 to the 7th. Geez, get it together, Ms. Schneider. And we get an answer of F equals 1.92 times 10 to the negative 12th newtons. So I was in fact correct that it would be a very small number. And that ends the section on magnetism. All right, the last section of the review is on optics. I'm going to go through these relatively fast because if you're still struggling with optics, there are lots of other videos of mine to watch, but I will still at least walk you through it. I'm going to use green for incident rays and blue for reflected or refracted. Remember that if it's a mirror, they're being reflected. If it's a lens, they're being refracted. So let's get started. This one is a convex. It's probably worth labeling. This is a convex lens. So for my incident ray, I'm going to go parallel to axis to the center of the lens, and then for my reflected ray, I'm going to go through the focal point. My colored pencils don't show up terribly well, do they? Then for my second incident ray, I'm going to go through the virtual focal point, which is this one on this side. And then straighten out to go parallel. The last line is always the easiest. You don't even have to draw the last line, but it's so easy for lenses that I usually do. It's just a straight line. We have a pretty clear intersection right here. Remember that you always draw from the intersection to the axis, and that the point of intersection is always the tip of the arrow. So, then we need to decide these three characteristics. For a lens, this side over here is where we expect the light to end up, so it's going to be real. It is below the axis, so it's inverted. And it is smaller, it's shorter than our original arrow. So there you go, real, inverted, smaller. This next one is a concave mirror. So our rules work a little bit differently. Parallel to axis, down through the focal point, down through the focal point, and then parallel to axis. The last one, well, you can't draw the last one for this one because it's on top of C. Normally the third line, if you wanted to draw it, would be through the center of curvature C. So there's our image. We can talk about it. It's on this side, and for mirrors, this is the real side, so this is real. It's below the axis, so it's inverted. It's actually really hard to tell here, but being on top of the center of curvature is a special point where it's the same size. That does not occur anywhere else. All right, here we have another convex lens. So it should work similarly to the one we've already done. But now notice that we've moved from way outside, out beyond twice the focal length, to between twice the focal length and the virtual focal point. So that's going to change at least something. But we draw the same lines, parallel. My arms are all in the way. Through the focal point, then through the focal point. You would stop where the mirror would be, even if the mirror doesn't go down, or the lens, where the lens would be, even if the lens doesn't go down that far. Parallel. And then your last one is simply my green colored pencil is terrible. Through the optical center, straight on forever. At least one of my, oh, this line, it's this line. This line isn't parallel at all. Let's fix that. All right, after a whole bunch of struggle that you luckily didn't have to watch and copious use of whiteout, I finally figured out what was going wrong with my third line. So now I more or less have a point of intersection that's way over here. So my object is going to look like, or my image, it's kind of worth labeling, I guess. That's the image and this is the object. On the performance final, I will be relatively lenient. If you have some struggles like I did, just make sure that you try to get things as parallel as you can. All right, so now if we're going to talk about this image, it's very similar to the one up here in that it's still real. It's still inverted, but now instead of being smaller, it is quite a bit larger than the original object. Sorry, so real inverted larger. Almost done, woohoo! This is a convex mirror. So it's going to work a little bit differently from the other two mirror, or the other mirror problem, but it follows the same steps. Oh, the lights turned out again. All right, so parallel to the axis. Then here's a kind of weird one. You line up with the focal point, but light can't go down through the mirror. It has to go up this way. For the second one, you line up with the focal point, but you only draw until you hit the mirror, because again, light can't go through the mirror. And then it goes back parallel. Those do not intersect in real space, but our brain wants them to intersect. So it extends them backwards, behind the mirror, like so. I'm getting an intersection somewhere around right here. You always draw from the intersection to the axis, and the arrow is always the tip, or the intersection is always the tip. So this is a very different image than any of the others. It's behind the mirror, so it's virtual. The intersection is above the axis, so it's upright. And it is distinctly shorter than the object, so it is smaller. Remember that this is the only type of image that a convex mirror or a concave lens can make. Only type of image a convex mirror or a concave lens can make. All right. Well, we have a grand total of 1 math problem, optics down here. So let's see what they've given us. A concave mirror has a focal length of 10 centimeters. If a 3 centimeter tall object is placed 40 centimeters from the mirror, find the location of the image and the height of the image. So here's what they've given us. Focal length equals 10. 3 centimeter tall object, so that's height of object is 3. The object is placed 40 centimeters from the mirror, so distance of object is 40. Now all of these are in centimeters, but we can leave them all in centimeters for this type of problem. If we go back to our handy dandy formula sheet, under optics we find that there's a formula that says 1 over f equals 1 over di plus 1 over do. There's a formula that's not on here, but that I will again have on the board for the performance final that says hi over ho equals negative di over do. So now we just have to plug numbers in. 1 over 10 equals 1 over di plus 1 over 40. 1 over 10 minus 1 over 40 equals 1 over di. There are multiple ways to go about this. I think the way that makes the most sense to most people, well, these numbers, it would be easy to find a common denominator and do it that way, but that's not always going to be true. So I'm just going to do it by plugging it into my calculator. So 1 over 10 minus 1 over 40 tells me that 1 over di is 0.075. That is not the final answer. You have to do 1 over 0.075 to get di, which is 13.3 centimeters. You can think about it as cross-multiplying. You can think about it as taking the reciprocal. Just remember that when you get to this step, you have to do 1 over this number to get the actual answer. Now we have to plug back into this formula. So we have hi equals ho, which is 3, and then this is negative 13.3 over 40. So if we cross multiply, we get that 40 hi equals negative 13.3 times 3 is negative 39.9. Divide both sides by that 40. And if you do a little bit of rounding, you get that HI equals negative 1.0 centimeters. Let's take a moment to talk about what these mean. The fact that this is a positive number means that it's real. If you ever got a negative number for DI, which is possible, then that means it's virtual. This number is negative, which means that it's inverted. Wow, that's some terrible writing. If you got a positive number for this, that would mean it would be upright. You're not going to have to write that on the performance final or anything, but it can help you be a little more confident in your answers, since we know that a concave mirror should create a real inverted image. All right, I think that's it. If you've watched this video and worked the whole thing, you should be reasonably prepared for next Monday. Feel free to email me with any further questions. I love you guys, and you're going to do great.